Good day, everyone. Today is October 17th, 2019. I'm your host for today's webinar, Mike Lasecki. Our topic is Integrated Nanophotonics, the transition to high-volume manufacturing and the implications for workforce education, presented by Dr. Robert Geer. We'll do introductions more in a moment. Let me remind you of a couple of aspects of this webinar. The webinar will be recorded. I've turned on the recording link, and will automatically send you a link to the recording. Please use the chat window on the upper right of your screen to ask questions, and at the very end of the webinar, we have a brief survey. We'll want to hear from you, just 4 questions, so please take a moment to do that. This webinar is hosted by ATE Central. ATE Central acts as an information hub for the National Science Foundation's ATE grantee community. You can find out more about ATE Central and their services, including their webinars, at atecentral.net. This webinar is brought to you by the NAC Network at Penn State University and the National Coordinated Infrastructure Southwest at Arizona State University. And this is a good time to mention that the opinions expressed by the presenters today represent their opinions and not necessarily those of the National Science Foundation. Let me start with introductions. Again, I'm Mike Lasecki. I work at Lookup Partners, and I'm the host of this webinar series. Also joining us today from the NAC Network at Penn State University is Professor Uzgar Kakmak. Uzgar, would you come along on and say hello to everyone, please?
Hi everyone, this is Oscar from Penn State. I'm an assistant teaching professor here.
Thank you for joining us. Uzgar, I think you were telling us that you actually are doing a graduate level course in nanophotonics right now, aren't you? I mean, you're teaching one.
Absolutely, yeah. This coincides, the title of the talk coincides very much with my research and also with my teaching interest too.
Well, good. Thank you for joining us today. And you and I will work with Bob as we get to the question periods, and we'll forward questions from the audience, and we'll have some questions of our own. Now, colleagues, our presenter is Professor Robert Geer. He's the professor of nanoscale science at SUNY Polytechnic Institute. And Bob, you're also the principal investigator of the NeoTech Center, headquartered there in Albany. So welcome, Bob. Say hello to everyone.
Hello, everyone. It's a pleasure to be here.
Great. Bob and Uzgar, your audio sounds good, so I think we're ready to begin our presentation. Bob, the outline is up on the screen. Take us forward.
Sure. Thanks very much, Mike. Thanks very much, Oscar. I'm going to talk today about integrated nanophotonics, and I'll get to the outline in just a second. This work, as Mike alluded to, has been supported by the National Science Foundation, and quite a bit of it has been supported in the past by one of the National Manufacturing Institute's AIM Photonics. So it's really been focused on that interface between transitioning technology to or developed technology into high volume manufacturing, and of course our focus here has been on workforce. So in terms of the talk, I'm going to start a little bit with what integrated nanophotonics are, or is, I should say, for those people not familiar with it. Do some comparisons with integrated circuits, which people may be a bit more familiar with, and then move on to talking about photonic integrated circuits, or PICs, and where we're turning the corner on high volume manufacturing, especially why now and not before. I'll refer to something called the design ecosystem for anybody that's worked in ICs. They might be familiar with that. And also a foundry model. And by that, I mean a place that, if you design a photonic integrated circuit, they will go fab it for you. That's a critical piece to the IC infrastructure now. We'll definitely talk about skills and tasks for technicians in this field. And I'm specifically talking about people or technicians involved in integrated nanophotonics manufacturing. A little bit about PICs versus ICs, not so much the difference between what a photonic integrated circuit is and an integrated circuit, but what different skills and tasks were required. I'm going to focus on a couple areas that are very distinct to integrated nanophotonics, that is assembly and test and packaging. And then a little bit on work that we've done here that's supporting AIM Photonics and a Neotech, a regional ATE center funded by NSF, on photonic integrated circuit testing, wafer scale and chip scale education modules in terms of quality control, and some advanced packaging work. Now, this is really at the sort of cutting edge of industry, so it's really focused on very hands-on activities that you would do with the integrated photonics industry as it stands right now. So in terms of, we always need a nice color graphic here and there. This is supposed to be part of a continuum that AIM Photonics, as well as the National Science Foundation, has been really behind for the last 5 years. And that is to try and get integrated photonics manufacturing workforce education on par with the technology itself. And so in addition to understanding what the technology is, also focusing on getting that information out into programs so new graduates know what it is and they can prepare to enter that career field. So before jumping into what integrated nanophotonics is and its manufacture, I'll talk a little bit on the history of integrated circuits. There's a relationship there. So first of all, I think everyone has multiple high-end chips on them at any given time if you're walking around with a phone and a tablet or a laptop. You know, rewind back to 1961, the first, not necessarily the first, but certainly one of the first substantial planar integrated circuits had 4 transistors on it, a whopping 4 transistors. Fast forward to 2018, and the I vanished on the IBM, not sure why, but that would be the IBM 7 nanometer node at the lower right-hand corner of the slide. So this chip has over 20 billion transistors in it. It's really a demo chip to demonstrate the impact of the technology. That's a tremendous increase by any measure. Of course, the famous Moore's Law, which got us most of the way there. But since, well, over the last 5 years, we've really been getting horsepower out of new devices, new designs, new materials, not simply just making devices smaller. Now, that's great in and of itself, and it's fine for the IC community, but we have to step back and think, what's that really enabled? So back in 1952, before transistors were available, or at least widely available, computing machines were built off, other switching components, vacuum tubes. Along came the integrated circuit, and fast forward for today, and now you have incredibly dense, high-performance computing systems which are spread out across the world, whether they're specific, like supercomputers that tell us what our weather models are going to be like, and easily predicted the rain we've been having here all day in upstate New York, all the way down to taking this incredible technology and shrinking it and putting it on a phone. And as I'm the father of teenagers, as some of you may be, I'm intimately aware of exactly how gripping this technology can be in terms of the iPhone. So if we step back, we see a tremendous amount of innovation, from the birthplace of this to where we are today. And this plot here is just a number of metrics. It's just a lot of nice colors, but it shows the incredible growth. I mean, exponential growth. So why show this? Because what integrated nanophotonics is really enabling is to increase this even further without changing the nature of the transistor. So photonics. Definition, physical science of light generation, detection, manipulation through emission, transmission, modulation, signal processing, switching, amplification, and sensing, all in one breath. So basically, moving signals around with light the same way we might with electricity. Now, I think we're all familiar with this, and if we're not, which is fine, we certainly use it every day. The biggest revolution associated with photonics, happened at the really end of the 20th century and the beginning of the 21st century, with what was a massive deployment of fiber optic network capabilities across the country, and across the world, I should say. And there's a great little graphic on the top of this slide showing you a cross-section of the undersea coax cable and what it was replaced by in terms of a fiber optic cable. So we're used to these tremendous informational transport speeds on fiber optic backbones. And so there's no question that part of photonics has had a very dramatic impact on how we communicate. Now, if we take a little bit of a closer look there, and none of this presentation gets overly technical, mostly because I'm a chip guy in my own background, so I'm a relatively newcomer to photonics. But in telecommunications, like what's on the end of those fibers, we usually work with whether it's a system from Cisco or any other technology provider. There'll be some components which take that light and code it with electronic signals coming from a chip or some other type of device, send it out through the fiber, and then decode it when it comes in. And so typically these devices are arranged on what look like a printed circuit board, and their sources, which may be lasers, well, are lasers, interconnects, which are typically the fibers, detectors, and coders, which are called modulators. So these are all separate pieces that may sit on a little board. Now, this is just a picture of what a discrete photonic modulator looks like. And remember, this is just the encoder. This is the encryptor. This puts those series of ones and zeros on that optical carrier signal. And one of the benefits of integrated photonics and what has enabled us to have 375 cable channels, if we wish, is the fact that we can put multiple colors of light through a single fiber, and they won't interfere. It's really a cool aspect of optical modes that they can do this. And the color piece is kind of it's a bit of a misnomer. They're really not different colors, but you can use different wavelength bands. And I don't mean bands that are far apart. I mean wavelength bands that only differ by about 10 nanometers. So imagine you have infrared light maybe at 1500 nanometer wavelength. You can have another channel at 1520, another channel 1540, and even shrink it down beyond that. So you can have multiple parallel sets of data going through the same fiber optic, traveling at the speed of light. And you can reproduce that, of course, in any type of waveguide. So that's a distinct advantage to be able to put more information through without significant loss. Now, integrated photonics. Well, it's just like integrated circuits. Sources, devices, and detectors on a single chip. Now, for circuits, we know that there's a plus to do that. So the question is, is there a benefit for photonics? So, but first, before we get to that, I want to go to Mike for take us into a poll.
Thanks, Bob. So colleagues, let's ask this question. What is the difference between photonics and integrated photonics, integrated nanophotonics? You can see the choices here. Integrated nanophotonics refers to photonic devices integrated on a single chip, or they don't include waveguides, or they always include transistors. So Bob, you can see that our audience is voting in the predominance. This shouldn't force you to change your opinion, everyone, but the majority of the question says integrated nanophotonics refers to photonic devices integrated on a single chip. Bob, would you choose that answer?
Absolutely.
Good, excellent, excellent. So good, that reinforces our discussion here. Now let's go ahead and go back into the presentation. And Bob, I'm going to move us forward and we're going to ask another poll question. So just a moment and I'll launch that second poll. Here it comes. So here's the question. In the context of integrated nanophotonics, what does PIC stand for? Bob, you used that term early in the webinar. Let's see if people got it. Abbreviation for picture, abbreviation for photonic integrated circuits, or positive index control. Bob, it's 100%. They got it. PIC stands for photonic integrated circuit. Excellent. So colleagues, thanks. Bob, we're paying attention today. Let me switch back to the presentation. I'll click forward one slide and tell us more about how to adapt silicon-based methodology.
Oh, thanks very much. I think what the polls tells me is everyone listening knows more about this than I do, so that makes me feel better. So I mentioned integrated photonics, you're putting it on a chip. And essentially, you could do that with any type of substrate or materials and so forth. I mean, we're used to working with fibers. They're made of glass. Silicon-based nanophotonics is very useful from a number of perspectives. The biggest being, people make silicon all over the world. So if you're going to pick and no pun intended, a choice for a platform to build the technology on, there's a lot going for silicon if you can get it to work. Now, I'm not going to go in the background science here. Silicon is actually a wonderful material, a wonderful wave guiding material for 1.55 micron light, 1550 nanometers, which is one of the major telecommunications wavelengths that's used. So it was actually a match made in heaven almost, that it works very well for silicon. So if you have this material that works well, at least for the waveguides, and you can get things like modulators and resonators, stuff I'll talk about a little bit more as we go forward. If you can get those all to work very nicely on silicon, then great. Okay, how does that help you really develop a new technology? First is to do with photonics exactly what you do with electric circuits, and that's what's shown here on the top of slide 16. Start with a layout. You put your devices using the same type of CAD approach you do for putting any sort of IP on a chip that you want to make, whether it's for a computer or whether it's for an alarm clock, what have you. Then, of course, you make the devices and you fabricate these. And that SEM picture there, a scanning electron microscope photo, is actually showing a series of silicon-based photonic devices. These are actually ring resonator-based modulators. And so if you see those two rows of rings and they're bound on either side by these little ridges, those ridges are actually waveguides or the integrated nanophotonic versions of a fiber. You go ahead and finish making your chip, coat it with whatever you need to coat it. And although silicon is a fantastic material in terms of propagating the types of light we use for these circuits, it's not a great material at generating the light. So right now, what people are using, I have a red circle on it, they actually attach the lasers, the light sources, directly to a chip. So it's a bit of a hybrid approach, but effective nonetheless, because other substrates, other materials make much better lasers than silicon can. So you go ahead and after you've manufactured, you test it, make sure it works, and you're left then with a photonic integrated circuit. So if we think about this, it really just has a few components on it. The silicon waveguides to replace the fibers, the devices on the chip, for example, like a modulator, light sources as lasers, well, they're not in the chip, but we can put them on the chip, and then I/O structures, input-output. The same types of input-output we have electrically, except in this case, we're doing it optically. So the reason is, we've been making chips for a long time. Why do we only have it now? So on the top of slide 17, on the right hand, I show you a couple close-up images. And on the left side of the image, you see this sort of gray band next to what looks like a circle. That is the functional part of what a ring resonator does. We have a light source or a light wave or mode going down that straight section of silicon that's standing up, and it will actually, through an evanescent wave, it will actually transfer that information or transfer that mode to that little ring, and we can use it like an on-ramp and an off-ramp. So that's how we move signals around. And in some cases, we don't just use silicon, we may use silicon nitride, but each of these things need not only be made in the shape, whether it's a circle or a straight line, but they have to have incredibly smooth sides and they have to be incredibly, incredibly uniform. To be honest, the lithography to do it this well didn't really exist. At least the projection lithography didn't really exist until about a decade ago. Before that, people were using electron lithography, which is incredibly slow. So these tools, which are all except the top, the 193 nanometer and the immersion lithography systems, they're actually both immersion. These tools are right now what's capable of making these. And these tools are also deployed in fabs around the world, with the exception of the EUV. There's only a few of those tools around the world. but they can make lines with this type of precision. And so, to be honest, why is transition to high volume manufacturing only happening now? One of the reasons is the fact that these tools haven't been around that long. So that's a huge boost, and that's what took this off, or really moved this from an academic exercise into into an emerging market. So a lot of other pieces are required here too, because one of the reasons that ICs are everywhere isn't because they're so great. It's because we have a design infrastructure that makes any reasonably competent electrical engineer capable of laying out a circuit. And we have people doing that all the time for all sorts of different companies. In fact, it's really democratized the nature of integrated circuits, is that if you buy a CAD package, computer aided design, and you know a little bit about the circuit you want to design, you can have a chip made. You don't need to know how it's made. You don't need to know exactly what the transistor looks like when it's on the chip. Just give the foundry a circuit and they can make it for you. And we don't have that. We don't have that exactly for integrated photonics, but we're awfully close. Some of these images you're seeing here on the right are actually the new integrated photonic layout type of tool, and where you can put these circuits down with a standard, what's called a process design kit, with a standard library of functions and devices. Now, once you have that, of course, you have to go to some place that can make it. So one of the things that I've had the luxury of having right next door to me is a fab here in Albany that IPM Photonics uses to make these photonic wafers. And it's a full functioning 300 millimeter silicon clean room, not too much different than companies like IBM or Intel would have. And it can turn these out the same way that a foundry, for example, in Taiwan turns out your iPhone chips. And then, of course, once you've got the chip, being able to hook it up to the world. That's a very important part of this, and that's actually a very challenging part of this, is to take what we can do with a photonic chip and efficiently link it with the electronic signals that are going to go into it or the optical signals that are go in or out of it. But altogether, these create an ecosystem, an ability for anyone to jump in and utilize and take advantage of the technology. Because that's the only way you go to high volume manufacturing, is making it suitable for a lot of different people to be able to use it. So, and I'm just gonna, you'll see this throughout the talk as I work through a lot of pictures. So this is an example of an electronic integrated circuit, or EIC, standing on a photonic integrated circuit, or PIC. There's a little close-up on the right-hand side of that of the different solder bumps used to connect the electrical signals. Optical signals go on through those tracks. And so this is something that can and has been done many times. And you can test these inside a printed circuit board. And it's this type of maturity, I should say, that is really necessary to make something, or to make a technology viable at a high volume level. So if we think about what this is going to look like, and I'm always thinking about this from an education point of view, so we've been talking about PICs, right? So we start with a piece of silicon in our case, and it may have lasers on or not, doesn't really matter. That might be our layer 0. And then we somehow connect it to something that allows us to get light in or out if that's the function of our little chip. So it might be a little sort of micro bench I have here. We can put that inside a package, something that will protect it, something that will make it mountable in another system. Put that onto a card, for example, and eventually, into something more complex. And I show the back of a photonics rack, quote unquote. The photonics is in quotes. Mostly what this is a rack that involves many different, both integrated circuit components, server blades, and what have you, and along with integrated nanophotonic elements. And I'll talk about at least one example of that as we move forward. So this is a picture of our system. Now, from an educator point of view, people need to be involved here at every step. No matter how automated it is, there's a lot of stuff we have to make sure works if that die on the upper left works in the system on the lower right. So Mike will take us into another poll.
Thanks, Bob. Now this one's a bit harder, folks, so which statement is true? about these devices that Bob has been talking about. Integrated photonics won't be introduced into the market until the next decade or so, or they're in the market now, or it's unlikely that they'll ever make it to the market. Bob, I have to admit, before this webinar, I wasn't sure where the product status was, but most of our attendees think they're in the market right now. Is that true?
That is true. That is true. Not a lot, but some, and they have an impact.
Okay, interesting. So that really updates my own information. I wasn't sure myself how much are they still in the R&D stage and how much they're emerging. So good. Colleagues, thanks for responding. Bob, I'm going to click back to the presentation. Go ahead.
Great. Thanks so much. I'll jump forward. Oops. I'll jump forward one slide here. So thanks for the transition there. Key PIC technologies. So the center says datacom and telecom. Absolutely where the vast majority of integrated nanophotonics lies. And to be honest, it's probably where the impact's going to be felt for quite a while. Sensors, because light is used for so many sensors in so many different applications, photonic integrated circuits has a tremendous potential there. And I don't mean potential like, 10 years from now potential. I mean potential like, people are trying to introduce products as we speak. And they're simple. They are, essentially integrating sensors and devices together for maybe disposable medical tests, blood analysis, things in which light are already used. It's just that they're not so small, they're not so compact, and they're not so inexpensive. So that is a burgeoning area. And if I can opine here a little bit, that's also an area which is critical for high volume manufacturing, because these types of sensor devices are usually built by small to medium sized companies. Until they're, the efficacy is demonstrated, they might be, licensed or picked off by a larger manufacturer. But this is why the design element is so important, because if it's a secret sauce that nobody can master, then why are you going to worry putting it in your, in your 75-cent sensor? The point is that anybody should be able to at least get some of the basics through, and that's why the design part is so important. There's a lot of military applications, mostly because it's high data throughput, and it can be incredibly light and low power dissipating. So when you are worried about how much energy footprint or just the size footprint, there's a lot of things very attractive about integrated photonics. And to be honest, any type of defense application is going to be built on transfer of a lot of data. It's a very natural thing for a light-based system. So Mike was asking, didn't know what was in the market. PIC technologies are in the market. There are definitely, if you are familiar with Watson, the various generations of IBM supercomputer over the year, yes, they use a lot of optical busing inside that interface directly with a chip to move that information around between the processors. But a much more common and application is called an optically active cable. So it's that picture on the lower side of the slide here. It looks like a regular cable you'd plug into the back of a server, and it does have the connector. It looks exactly like that. But that's not an electrical cable. That's a fiber optic. And so inside each one of the ends is an integrated signal modulator that will take that electrical signal, convert it to optical, send it through the cable, convert it back, and send it in. And the question is, gee, is all that worth it? Well, when you think about what really drives, there are two costs which drive large data farms. One is the power to run the chips, and the other is the power to cool the chips. And so this reduces a lot of, first of all, it reduces a lot of heat dissipation, and it increases signal time. So the delay from one blade to another is substantially reduced for this optical fiber versus a type of coax cable or Ethernet. So that's one of the reasons it's being used. So I'll stop or pause here on the photonic integrated circuit and IPM intro and overview if anyone has any questions.
Bob, it's Mike. I'm going to ask Uzgar to moderate the questions. Go ahead, Uzgar.
Okay, thank you, Mike. Yeah. So during your talk, we received some questions. Let's start with Aju's question. We know that we'd like to achieve the best resolution, like with e-beam lithography for our silicon chips that we use in electronics. But like, do we have like a similar fabrication tolerance with these kind of technologies that we're covering here today too, in terms of the
Yeah, that's
resolution
an
and the performance?
absolutely essential. So luckily, and I mean, this is a lot of hard work by a lot of people over the years for the IC industry. Um, the type of resolution needed for, say, the 20 nanometer node, and most of the high-end products we use now, actually it's 22, are made with the 22 nanometer mode. Um, that those tolerances are well suited for integrated photonics, very well suited. And the higher end processes are 14 nanometers. Um, they work even better. So now you have to be in an advanced fab. So to be honest, just not just any fab would work. But right now we do have most of the fabs available for the large manufacturers and the large foundries. TSMC out of Taiwan, and a place like Global Foundries, who used to be AMD here in the US, they absolutely have the right technology to do that.
Mhm. And another question was came from Tony. He was wondering if you kind of briefly mentioned this too, but if it's nanophotonics, integrated nanophotonics is strictly based on silicon or not.
There are a number of different, and this goes a little bit outside my expertise. There are a number of different platforms, including some of the platforms which make really good lasers, 3,5 materials, indium phosphide. And you can certainly create very high quality, high performance integrated photonic circuits in those systems. The challenge is that they just don't have as large a manufacturing base. So I think anything that's going to drive a widely used or widely scaled product is likely to come from silicon. But there are absolutely other material systems which have a lot of advantages. It's just that they're not so mature in
Hmm.
in the manufacturing side.
Right. So, Mike, how's the timing? Should we go on with a few more questions, or should we leave them for the till the end of the talk?
Let's take two more questions, Uzgar.
Okay. So, Roger was wondering, you mentioned like why are we adapting everything for 1.55 micrometers in our integrated nanophotonics?
Great question. Well, firstly, there are two major telecom bands for just for fiber communication. That's 1.3 microns or 1300 nanometers and 1550. So not that you have to do that, but that works. And also, silicon has a nice sort of window, absolutely at 1550, and to a certain extent at 1300. So it is very transparent to that infrared light. And that just happened to work out. So a lot of the fabrication that we're doing here with AIM and that I do with my students, is focused purely on structures that are good for 1550 nanometer light. There are definitely other applications, and I think more of these, some of the medical and biosensor applications where you wouldn't want to use that. You want to go with visible. And absolutely there are options there too. But I think some of the higher volume applications are likely to stay in that 1550 range or 1300.
Yeah, one last question because of the timing. General like bottlenecks for end-to-end optical communications, what would you say?
Oops, wait a minute, I missed the last part of that.
Oh, yeah, the bottleneck for end-to-end optical communications in integrated nanophotonics.
Sure. In terms of anything that involves interfacing one medium to another, and even though they all may be, silicon or silicon oxide, interfaces and any type of connectors are a real challenge. They take a lot of work, and that's just in the optical side. Of course, then you also have to worry about making sure that you've got a good electrical connection because the electrical circuits are driving the encoding and the decoding and so forth and so on. So, but I have to say, people apply themselves to these problems, and they've been able to really get them down to losses down to tolerable levels.
Okay, thank you very much. So I think we need to continue because of the timing restrictions, but we will come back with the other, try to answer these questions later on.
Great. So if that was an intro to what the technology is, which I spent a long time doing, the question is, do we have the skill we need? Do we need people more specially trained in this? What do you need to be able to do? And luckily, we're not starting from scratch. Um, you know, integrated nanophotonics is no different than any other advanced manufacturing. There's a sort of manufacturing path, going from the R&D level to product, even for a mature technology, and that's sort of paralleled in the education prep. In other words, for the R&D, you typically work with people which have a more in-depth preparation education. They can sort of they're trained to deal with the varying types of requirements in terms of working out an R&D issue. And then, of course, as we move into the manufacturing and the tasks become more specialized, that's absolutely the province of 2-year and 4-year education. And on the left side of the slide, I give just some examples, whether it's manufacturing, assembly. KGD means known good die. In other words, testing what you just made to make sure it works before you put it in assembly. Now, the majority of this range here is dominated by 2-year degrees, whether it's in the manufacturing, assembly, and so forth. And if it's not dominated by 2-year degree, those are where the skills lie to essentially to support these areas. Now, just in terms of, how do I compare this to what? So pick manufacturing. There's a lot of overlap with IC techs. It is likely to be highly automated. So your techs may not even need to know much about the process. They're going to support the tooling. And so it'll be very similar to what IC techs do now. Now, once we go down to the sort of a pick assembly, and I'll get a little bit just in a slide or two, the difference how I talk about assembly versus packaging, for those of you with some background in it. But pick assembly, there's actually a fair bit of overlap with IC technicians, but there's also a fair bit of overlap with photonics technicians. And what's the difference? Well, photonic techs are going to be people that do the manufacturing and testing of these discrete components, people that are used to working with lasers, used to working with optical benches, used to doing measurements and tests and quality control. So if we go down to the package level, we see that, to be honest, there's more overlap with photonics techs than IC techs. So we've got this very interesting little spectrum here. And to be honest, the skills are out there. It's a question of maybe, giving one group these skills that other groups have had in terms of, prep. So I'm not going to read this on the next slide. There's a lot of things a semiconductor manufacturing technician knows or needs to know, and have a lot to do about the tools, has some to do about the process. So if I say, well, geez, if I'm going to start as a base, what does an integrated nanophotonics technician need to know? To be honest, it's the optical side. And even if it's highly automated, they need to do tests to verify that these structures work the way they're supposed to. So there's quite a bit in terms of electrooptic testing. And once you get them and test and say, oh, this chip is working well, you have to interface it. Now, for anyone that's worked with chips in their lives, maybe know a little bit about solder bump bonding or wire bonding or these types of things. It just gets that much more challenging working with photonic integrated circuits, depending on how they're designed. All right, so there's a lot of other aspects of the reliability that is unique to IPM or unique to photonics. But definitely the PIC testing and the specialized assembly and packaging are those skill sets that need to be added. So I'll try to add a little flesh to these bones and maybe give a miniature or micro case study. So 2 types of IPM technicians, right? Maybe one that's supporting equipment in a fab that can do photonic integrated circuits. And to be honest, it's going to look an awful lot alike IC techs. And in some cases, there may be no difference if they know what structures, if they actually know what's going into the tool. Now, we move on the other side of the spectrum, or a little bit farther away, and that is techs that might be doing the hard part, testing the chips, assembling them, packaging them, and making sure they work. So these are going to be a high overlap with photonic technicians. So if we think of these as two ends of the, or two bookends on the shelf, or two pieces of bread on the sandwich, these are going to capture most of the skills that are needed by technicians moving into this field. And let's focus on that second one first, integrated photonics test, assembly, and packaging. So what do I mean by that? This doesn't differ too much from regular ICs. You fab your wafer, right? And it's got a bunch of different die on it, and then they're copies of one another, or they may be different, this depends. And each one of these has to undergo some sort of wafer scale testing. Now, the wafer scale tools for the optical side don't really exist yet, but they're being built. And so those will be available. But we definitely have, in working with photonic integrated circuits, we may want to connect those to other types of circuits. So we put something on top of it called an interposer. And this might be another layer of silicon with little wires through it that we can connect and put a integrated circuit on the back of. So interposer is something, you can think of it as a separate layer step that goes right on top of the entire wafer. So we can think of this as a wafer scale package, at least that's what you might call it if you were in an IC fab. And then cutting up the die. And cutting up the die means they're getting ready for individual packaging and assembly and so forth and so on. So there's a whole set of wafer scale assembly and packaging steps that would largely happen in the fab, and this would be on that sort of fab technician side. Now, if we think of what happens on the chip scale, and this is after they're singulated or after the wafer is diced, then we've got the chip scale testing to do. Maybe similar testing, maybe different testing. Fiber and laminate attached. This is actually putting it into packages. And so then, of course, is surface mount assembly. Now, for ICs, it may have been something as simple as gluing it to, to a polymer package or to a ceramic package. It's going to be more complex for the integrated photonics because we might need to get fibers to them, all right, or fibers out from them, or whatever you might need. So it is going to be more complex. So if that's our backdrop of exactly what I mean by test, assembly, and packaging, and there's various tests that go throughout all of those, then we can think of what the technician needs to do. Now, I'm not going to go through all of these. These are 8 areas that we identified a couple years ago working with people at other NSF centers, Gordon Snyder and Dan Hull, likewise interfacing with the people at AIM Photonics. And I want to use at least some specifics here, number 4, and think a little bit more about this in terms of work functions, like what would you have to do? And so this is built off the work that largely has happened here at AIM Photonics, and that we know with some of the companies, actually a lot of the companies that work with AIM, utilize these steps, and a lot of times they'll have technicians doing them. So how about a critical work function? So if I'm doing integrated nanophotonics and I'm a test and assembly technician, what am I going to be doing? Well, very simple. I'm going to have to align and somehow 3D bond various die on a photonic integrated circuit. Now, as I alluded to earlier, this could be a laser, all right? And then that's work that has been going on for several years now. Or, maybe more commonly, I've got to put an integrated circuit on it, right? So this might be the integrated circuit which processes information that comes through the fiber optic, or through the integrated photonic chip, or sends information out through the integrated photonic chip. So you're going to operate some sort of micro-optic pick-and-place equipment, bonding and attachment. You might have to do underfill depending on how you attach, if it's electrical. And so these are, if they're not inline tools, they might be nearline tools. So that's something that one of those techs will have to do, and they'll have to, of course, do whatever post-operation metrology to make sure it works. Alignment and bonding of various die on passive or active interposers, complex sounding thing. And there's a picture I showed earlier. Essentially, if we're using an interposer, it's like a miniature little circuit board, but it's made of silicon. and I can attach several things on either side of it. And so it's going to be sort of the alignment and 3D bonding on steroids, because I might put several components on it. So that means I have to go back into my tool, evaluate if it works, and not just a chip, but a laser source. In other words, it's something that couples optically into a chip, just electrically. And then that can easily be more challenging, since I can lose a lot at optical interfaces if I'm not careful. Last, but not least, maybe 3D inspection. And this is going to be a different type of inspection. Much of it's automated for chips. This is unlikely to be as automated, for the near future anyway. So to make sure that everything is aligned, and I expect operation. So those are an example of 3 tasks. If we think of this, and that's more on the fab side. If we go away from the fab side, this was labeled critical work function 4B, if we go away from the fab side, it's just, closer to the product. Taking whatever, structures you have on your interposer, for example, and putting them in a package. And I have some very simple photos here of these types of, these type of packaged PIC elements. Putting them into a package, alignment, wire bonding, fiber connections. These are things that we expect from a normal photonics tech, or people that have that background in training. So this is much more along the line of what a photonics tech might do now, except they're working with these integrated structures. So if that's an example, it's not exhaustive by any stretch. If that's an example, okay, where does this fit in terms of training? In other words, if I wanted to find a program, 2-year program, what have you, what would it be? Well, so that's actually been an area of effort too. On next slide, or on this slide, if you're familiar with these multicolored pyramids from DOL, that really these competency models, and I give you the definitions I give the tier definitions here, where do IPM or integrated nanophotonics fits? Well, to be honest, the industry sector competencies really haven't been codified for semiconductor manufacturing, much less integrated photonics. But we can essentially build on the existing models that have been developed under SEMI and Semitech years ago. Certainly a number of the ATE centers, Maytech, foremost among them, that's developed this, and simply layer the IPM technician skills and competencies on top of it. But there's another question to ask, and the idea is, well, under the industry sector technical competencies, that upper yellow tier, are industry-wide tech competencies, and so you might cast a wider net, like including all of IC manufacturing, or including all of advanced manufacturing. So the question is, are there sufficient foundational skills in this? And it's not a question I'm going to answer. I think it's more of a question for people to think about. There are some data literacy demands for techs working in this, because reliability is an issue, statistics is an issue, process control is an issue, the way it is in a lot of other advanced manufacturing fields. Also, there's a design element here, because some of these elements of design are they really, they might be accessible to a 2-year degree. Maybe we should think more about that. Those aren't questions for us, but those questions that naturally arise when you're talking about something like the integrated nanophotonics. So if we think we're going to sit pretty much in that advanced manufacturing sort of tiers and shade over to something a bit more specific like IC, I think that we can find an area where the integrated nanophotonics will fit. So at this point, I do want to stop to see if there's any questions on any of the tech skills, at least just a few that we've talked about so far.
Uskar, there you are. Hi.
So we've got 2 main questions. Actually, I tried to answer Rick's original question, but you gave a much better and more complete answer to that. Rick was wondering, like, at the very initial stages of the presentation, would employers hire technicians with only a 2-year degree or certificate? You showed us like those 4As, 4Bs, how they can contribute, and I just covered only the optical table aspect, but from the perspective of an academician, but you gave us how answers how these manufacturings and other related tasks already available in the curriculum might be also very handy. But Tani was also wondering um, what would make the most sense in a two-year college? Would we need to create a standalone nanophotonics program, or should we add a couple of courses to the existing program, like in the case of electronics program? What would you say?
I think that's a fantastic question, and I'm going to give you my very biased view.
Hmm.
And this is coming from someone on the semiconductor side, that narrow programs never seem to do that great. Even if they do well for a while, but that employer fills their need, what have you. Um, I think that you're much better off in taking a program that's got a wide, sort of a wide, a desirability among students, and inserting components as long as you can fit them. And there's always a struggle, right, between stuff that's already in the curriculum and taking it out, and there's all sorts of issues with that. But a lot of these skills that you need are very broad, and then you just need to add that, that little depth here and there. And so I think a good strategy, no matter what, is to take some of the degree programs, whether it's electrical engineering technology, for example, a two-year program I'm very familiar with, and then adding some of these components that make it a good fit for IC, adding some of the components that make it a good fit for the nanophotonics. Because at the end of the day, you're going to use that platform and build with your sort of on-the-job training to solve their particular issues. So I think, I just don't see a demand that's going to be so rigid and so narrow to where it said, hey, come and get my AAS degree or AS degree in nanophotonics. I'm not sure that's the best way to go. So I really do believe that, keep it broad, but make sure you get some of that key content in there.
Wonderful. Thank you very much for these answers. And I think we've got a little bit more slides ahead of us, so we can continue.
Okay, I think there's only 87 slides left to go. I'm just kidding. So let me tell you, along that line, what have we done? And by we, I mean working with AIM Photonics, working with the National Science Foundation, and some of our partner community colleges here. And this is not necessarily an example of what you might do, because we're working with equipment that we have access to here, but that's the whole point for us. We wanted to, not show that this is something that would work for two-year techs. We knew that would be the case, but finding a way to get these people the experience on this type of tasks and this type of equipment. So we developed a bunch of course elements, and they're not courses. They're more modules. For that same reason is we're not going to have someone rewrite their entire degree program. So on this slide, I list I have 6 different topics, going from a general type of technology overview. Something you might give more. You do your first course on what may be integrated circuit manufacturing, if you have that, or just advanced manufacturing in general. And then talk about some process basics. And I'm using the term process very generically here. These are more underlying topics and skills. So they might be the basic optics that you need, working with optical components. They might be the basic processing. If you're going to be on the fab side, you might be the basics, whether it's vacuum technology or what have you, about how you work with these tools. Specific manufacturing process flow and systems modules. That's just going to be a silicon-based, integrated nanophotonic manufacturing type of flow. The last 2, 5 and 6, are very important. Assembly, metrology, tests, and quality control, because you do that in almost any advanced manufacturing field. And then practical training courses. And these are key, getting people hands-on training with it, because it demystifies a lot of the technology. So for the last few slides in the presentation, I'm going to talk about stuff that we developed. And we have used all of it with, some selection of undergraduates and two-year college students, right? So they've had their hands on this. And we really started from the very practical end. So if I jump back a slide, we started it at number 5 and 6, if you like. So we actually designed and fabbed a whole series of integrated photonic chips because we have the fab here. And we worked with students to, okay, get hands-on experience in testing. So the first chip was actually doubled as just a health aligned chip for us, and it's all that purple stuff you see in front of you. Just a whole bunch of different integrated photonic structures. And they're passive in that you don't need any electrical circuits to measure these. You can just measure them with light. So we designed that here, and you see, when I move to the next slide, some examples of what that means. These little spirals, although they're a nice pretty color, they're nothing more than waveguides. And if you look really, really small on the bottom of the slide, you might see that each one ends in two little arrows. And those are just grading structures where you shine a laser. And it's very simple. You shine a laser in, and you measure the laser out, and you measure how good your, in this case, waveguide is. It's no different than a fiber measurement, except this takes place on a chip. So this is what we've gave both undergraduates here in 4-year degree programs and to your college students experience in doing. And it's a straightforward measurement. I won't go into the details, but we had experience on this. And of course, unfortunately, the measurement platform is relatively expensive. You know, that's just the nature of the beast here. But the wafers aren't that expensive to fab. So what students would do is they would learn how to, and I'll use the cursor here, they learn how to line the fiber probes on this station to a particular grading inlet to the waveguide, and then put another detecting fiber on where the light was going to exit the waveguide. And you can give them experience in aligning it, which is a non-trivial process. What probe configurations you use, how to do it safely, how to not damage the probes or the wafer, both wafer scale testing, in other words, working on an entire wafer, but just doing individual measurements, as well as chip scale testing, working on a little chip that might be in a package. So we had students get experience with both of those things. And you know, the outcome may be really something like this. Not that technicians are looking at graphs all day, but they are looking at numbers. So this is an example where on the lower right, we had students measure a loss, which in this case was about 1.5 decibels per centimeter, actually a pretty good number. And they learned how to acquire data. They learned how to essentially, and much of it's automated, learned how to documentation they needed. And they learned some very, very basic statistics in terms of how error bars were generated, and they would create the document for, you know, like an engineering team report. So that was work we've done in the lab, and we did some custom development to make this, you know, very much like a formal measurement. I just put this up here just to advertise the work of one of my graduate students. So there's a nice user interface, you know, programmed with Python. So we did this, we worked on this both last year, and we have some more work this year. We worked with students from Fulton Montgomery Community College, which is out in sort of east central New York. And you know, the students did a very good job. Now, we've taken this, you know, further along this direction by expanding the number of devices, and I'm not going to go into it, but each one of the measurements we have here takes a slightly different skill and uses a lot of the equipment that you might use in an IC fab, except it's sort of tailored for integrated nanophotonics. And on this slide, we'll see a couple little schematic elements of, in the center here is the gradient, so that's how you get light in. Some coupler structures, some ring resonators. I showed you a picture of those earlier. Doesn't matter if you don't quite remember it. But experience in measuring all of these. And there's a reason why, and I'll mention that. The reason why is that these types of structures, and on this slide I'll show you some of the second chip, the second wafer that we designed for test structures. These types of structures, you see these little squigglies here, are exactly what you need to create most types of multi-wavelength integrated nanophotonic circuit. And depending how you make them, you have to test another one. I mentioned before, the automated technology to do that testing is close, but it's not there. There are no tools that are out on the market yet. There are some that are in beta testing. So this is left to technicians at this point to do. So we take these designs, turn them into wafers, and we measure. And so on this little picture here you see a picture of the probe station, but where my cursor is circling, this is actually a response out of a ring resonator. And so it's got a bunch of squiggly lines up here with these dips. And these minima here are the notches essentially that would pluck out a signal from one color band to another. And so that's exactly what this structure does. So if these notches here, say this one that's close to 1500, one at 1520, and so forth and so on, if they're not uniform across the wafer, then your device on one side of the die will not work the same way your device on another side of the die works. That's bad news. So techs need to be able to qualify this and say, okay, I've got a very stable process. Everything's looking good. Specifically, though, they are going to look at, these, overlays of a lot of different data. Some of this can be automated, some of it can't. And if they're looking at data across the wafer, they need to know, okay, my wafer is in spec here. And separately from integrated circuit measurements, one of the things that plagues, not plague is the wrong word, one of the things that can happen in a fab if you're not careful is that these devices on one side of the wafer may work different from the devices on the other side of the wafer, and that's not good either. So, for example, what techs may have to do is generate reports of just how this varies across a wafer. And these variations here, these bars, are nothing more than how that notch moves. So the 1520 nanometer notch, okay, that's going to grab light at 1520 nanometers as it moves through a waveguide, right? Okay, if it works, if it's tight on one side of the wafer, but it's less tight, 25 centimeters away, we've got an issue. And that's exactly what this plot looks at. And so you have spec bars, the same type of statistical analysis that techs do in the integrated circuit industry all the time. That's definitely something very important for integrated photonics techs. Right now, what we're working on is going one step further, and that's active devices, where you actually have to, use an integrated circuit, say network analyzer, because you're driving circuits that may be like a modulator. So this would be a chip that would encode information into the light, and you have to make sure that this device is working appropriately. And so I won't go into the operating principles of the device, but testing them are very important because they're the lifeblood of encoding digital information in a light wave. And so these are the types of devices we're looking at now, where we have a whole series of these across the wafer, across the die, I should say. And we'll be doing the same type of testing, and we'll be engaging community college students to do that type of work too. Now, once again, this is very expensive equipment, so it's not like you're going to put it into your lab. But these testing capabilities are really very similar to what photonic techs do now, and I'm very very positive that there'll be some good ways to integrate some of these devices in a very cost-effective way in curricula as we move forward. So a last piece in the last couple minutes, and I'm sure I'm over some sort of time, but I talked a lot about assembly, and that's actually another very important part for techs, a little bit less on the optical measurement side, but extremely important, because when we talk about reliability, how you assemble it is everything. It's critical. And so we've done a fair bit of work on just 3D ICs in general, stacking, interposers, these types of things. And on this slide, I just give you some content that we developed here at SUNY Poly, and some hands-on labs that we've had community college students work on with some of my students. And that's essentially using IR microscopy to look straight through stacked wafers to make sure they're aligned. In this case, it wasn't, but that's okay. And looking at getting some experience with what happens when you bond individual die to an underlying wafer. It's really nuts and bolts stuff, but it's very important for students to get hands-on experience with. It's not something you need a course on, but it does make an outstanding capstone type of experience. And one thing that AIM Photonics has been working on with partners around the country is to get these labs up and running so that two-year students in programs nearby can come and take advantage of them, and that's what we're doing here as well. So, in terms of summary, I hope what's come across is that integrated nanophotonics is absolutely turning the corner towards high volume manufacturing. And that's definitely I think a key takeaway I'm hoping people get here. And a lot of the pieces are in place. Design tools, initial foundry models, whether they're here in the US, whether they're in Europe, and there's cropping up all over the world. Um, the tech skills for, ooh, that should be IPM, not IMP. The tech skills really cover a lot of what already is being taught in maybe photonics and laser programs for techs, as well as what's taught in programs that sort of skewed more towards semiconductor manufacturing. There's a lot of overlapping skills, but there are also some unique combinations. Likewise, in terms of tech module development that you'd like to adapt to that, or you'd like to be able to apply to that, I mean, we've done some initial module development, and a lot of other institutions working with AIM Photonics have, both complex and more basic. And so it's just like a lot of things, it will take time to find really good sustainable approaches to get some of this into community college courses or two-year college courses. I think it's eminently feasible. I think a partnership model can work well for that. So with that, I'll go ahead and close. Thank everyone for their attention. And I don't know what sort of time is left, but if there's any other questions, maybe we can speak to that now. Thanks very much.
Bob, it's Mike. We do have a few minutes, and we're slightly over, and if people have to leave, that's okay. But we have a couple of questions I'd like to bring forward. Let me start with one, and then I'll turn to Uzgar. One question is, do you think one approach might be to integrate this into a two-year program and then maybe have a certificate of some sort that demonstrates skills and competencies in this area, some sort of credential that an employer might recognize? Is that possible?
Well, no question. In fact, we worked on an approach like that, early on in AIM, so we developed these materials for some specific credential. Just like a lot of things, though, and this is probably more of an issue for New York State here, and I'm at a SUNY campus, where it's that's a lot of activity, or that can be a challenge to go through the review process and so forth, unless you have a large number of students using it. What has really come to the fore, at least in our neck of the woods, is these aspects of micro credentials, which actually look more like a minor, and they're maybe 12, 15 credits. I think those are perfectly aimed at this. It's something a campus can do on their own. It can show up on a transcript if your institution happens to do that. And I think something with that, with a low entry threshold like that, it really works well for an emerging area like this, because the job numbers aren't going to be overwhelming, but there are definitely people that might want it. So I think there are great academic credentials that individual campuses have the ability to do now.
Good. Thank you, Bob. Uzgar, do you have a concluding question or two for Bob?
Yeah, one last thing. Actually, Jay raised this question. Jay and we saw that you have these nice active devices in your PDK version 3.0 in that AP SUNY PDK. Is that open to everyone's use, or yeah?
So well, you certainly can. I think you can get access. The access to the PDK is through Moses, if the person's familiar with that. So that's been around for a long time. And if you do want to have devices fabbed, then there are multi-project wafer runs, and it's not the cheapest thing, per square millimeter, but it's not the most expensive either. So if you can cobble enough people together and pay your 15K, 20K, you can get a few square millimeters, and it will be the design will go through Moses. It'll be design checked. Will be fabbed, and then I forget the number of die that you get. It will be diced off and sent to you, but that's about the extent of the packaging. There is a new packaging facility that AIM is opening up out in Rochester. I couldn't tell you if that's customer ready yet. It's darn close. But anyone can get access to the PDK, and then, of course, you pay your money for the fab.
Thank you very much, Bob. This was a great, very enlightening presentation. I wish I was a student at this time. Yeah, we learn many of these things just theoretically and in a simulation manner. It's really good that students can feel them and measure them.
Yeah, that's true. It's a little disappointing when after they measure it for a while, they sort of just always they expect it to work all the time. And I try to tell them, you have no idea how difficult it is to do this. You should be really appreciative. And, then they roll their eyes and get back to work.
Right.
So it's something
Hmm.
like that.
That's good, Bob. Uskar, another thing that struck me in Bob's presentation was a couple of things. One, the need for data literacy, right? As we looked at some of those graphs, what the students had to be able to know and do when it came to acquiring and talking about data. As you know, Bob, that's such a big driver for a lot of things today. I was very pleased to see that in your presentation, and I was really unaware of how many hands-on learning activities that you've developed in this area. So that was quite really good today, Bob.
Oh, thanks very much.
All right, colleagues, let me just, as we wrap up today, thank you for your patience at the very end. Let me just pull up another screen that says join us. The screen is just coming up now. It says join us on February 20th, 2020. Isn't it amazing to think that's next year and it's not that far away? 1 p.m. Eastern. Here's the title of our next in our webinar series, Multi-Responsive Nanogels for Biosensing, Drug Delivery, and Regenerative Medicine. I have to admit, I don't know much about nanogels, but I think they can be really custom engineered to do a variety of things. Our presenter is Professor Clegg. That's right, excuse me, I forgot his name for a moment, from Harvard University, so we're looking forward to that. Now back to the presentation screen, and we'll wrap up for today. Thank you again, Bob, for the presentation. The slides, just great. Remember, this thing was recorded, folks, and you'll get the recording link as well as the slides. And now on our last slide, I'll move forward. I'm going to launch the survey. It's just 4 questions. It opens in another window, so don't worry about that. Just go to that window, and then you can close out of the system. I'll leave the system open up for a few more minutes. So here goes the survey launch. Bob, thank you again. Uskar, thank you very much for the commentary today. Really appreciate it. Colleagues, the survey is now launched. So thank you for joining today. This officially ends the audio portion of our webinar. Goodbye, Bob, and goodbye, Oscar.
Bye.